Ladies and gentlemen, please welcome AGU President Michael J. McFadden.
Thank you and good afternoon. Thank you for joining us today. Tornado swarms, hurricanes, droughts, and floods. This year, the U.S. experienced a record 12 weather-related disasters, each costing in excess of $1 billion. One or more of these events may have affected you or someone you know. That's why the topic of today's lecture is so important: predicting and managing extreme events. It's also why I'm so pleased to welcome Dr. Jane Lubchenco to the 2011 Fall AGU Meeting to deliver the Union Agency Lecture. Dr. Lubchenco has been the Undersecretary of Commerce for Oceans and Atmosphere and Administrator of the National Oceanic and Atmospheric Administration since 2009. A marine ecologist and environmental scientist by training, she was nominated by President Barack Obama in December 2008. Dr. Lubchenco has served as president of the American Association for Advancement of Science and is a member of the National Academy of Sciences. She has received numerous awards and founded the Leopold Leadership Program at Stanford University. As president of the American Geophysical Union and a NOAA employee, it is my distinct pleasure to welcome Dr. Jane Lubchenco.
Hello, everyone. Are you out there? Hello. Thank you, Mike, very much. I appreciate that warm welcome. It's a great pleasure for me to be here at the AGU Fall Meetings among so many good colleagues and friends. I want to, before I begin my formal remarks, just take a moment to thank the leadership of AGU for everything that you are and have been doing to be good champions of science and to focus attention on its importance and its relevance in today's world. Science really underpins all that AGU and NOAA do. We share a commitment to science, and we share a passion for protecting the importance of scientific integrity. I believe that scientific integrity is really at the core of producing and using good science. And so I want to begin just with a very brief update on that front. When I first arrived at NOAA, I made a commitment to protect scientific findings from being suppressed, distorted, or altered, to strengthen science, and to encourage transparency in the use of scientific information. From my first days on the job, NOAA has been working hard to develop its first ever policy on scientific integrity. This policy is about fostering an environment where science is encouraged, is nurtured, is respected, rewarded, and protected. And in that spirit, I'm pleased to tell you that today, after my remarks, I will be announcing the formal release of NOAA's first ever policy on scientific integrity. This policy has been developed through an inclusive, a deliberative process that I think has served us well. It's something that the agency is proud of and that we own. And this policy really amplifies both NOAA's and the Obama administration's commitment to scientific integrity. So now on to the focus of today's remarks. I want to begin with sort of a broad lens and just acknowledge what a challenging time this is for the nation and for science. Excuse me, for science. The economy is in bad shape, although it's beginning to show some positive signs. Extraordinary numbers of Americans are without jobs. The public holds a record low opinion of government. Our science is being questioned, and the pressure to reduce federal spending is intense and intensifying. The irony is that the demand for the kinds of services provided by agencies like NOAA is at an all-time high and is growing. One reason for this demand is the increase in the number and intensity of extreme events. From heat records set in every single state this year, and at one time during the summer, over half of the number of people in this country were under a heat warning or a heat advisory at one time. To last week's hurricane-force winds that hit parts of California, Utah, Nevada, Arizona, New Mexico, and Wyoming, with winds that reached 97 miles per hour in Pasadena. NOAA has been very, very busy predicting the weather-related extreme events we've seen this year. However, our capacity to continue to do so is seriously threatened by the downward pressure on our budgets. Both budgets and politics threaten our observations, our research, our modeling, and the delivery of information and other services. Our ability to do these kinds of predictions and to fund research to improve our ability to predict even better by understanding the causes of weather extremes, for example, and our ability to improve the effectiveness of response to the warnings through social science research are all at risk. Today I'm going to focus on some of the unusual weather patterns we've been seeing and what I believe we need to do to better protect and to manage them. Better predict and manage them. And I hope that you will be willing to work with us to innovate and devise new approaches to tackling some of these big problems that are out there in ways that are commensurate with the budget and political challenges that exist. In his introduction, Mike mentioned the 12 events, billion-dollar disasters this year. I want to give you a little more information about that, but just begin by acknowledging that the year 2011 is already in the record books as a year of historic extreme events. One of those new records is the number of events that total at least $1 billion in damages. Today, NOAA is announcing that in 2011, to date, there have been now 12 extreme weather events, each totaling at least $1 billion. The previous record was 9 events set in 2008. These 12 events are depicted on this slide. Earlier this year, we announced that there were 10 to date, and as we keep doing the accounting, there are more and more that emerge. And so we are now up to 12, but I emphasize we are still counting. The 2 new ones, number 11 and 12, are the June 18 to 21 tornadoes, and we've now split the spring-summer drought heat waves in Texas as a separate event from the record Texas wildfires during the summer and the fall. The aggregate damage from these 12 events is approximately $52 billion. We have not finished tallying damages caused by additional extreme events, such as the pre-Halloween winter storm that impacted the Northeast and the wind flood damage from Tropical Storm Lee. So stay tuned for the final total of the number of $1 billion events, as well as the aggregate damage. I also want you to note that the damages totaling less than $1 billion individually are not included in this tally, even though many of them represent additional significant financial losses. And of course, the economic losses are far from the full picture. More than 1,000 people have died from these disasters. Deaths this year are almost double the yearly average. Each of these events is a huge disaster for victims who experience them. Collectively, they are an unprecedented challenge for the nation, for the safety of citizens, the bottom line for businesses, and the social and societal stresses that they engender. Timely, accurate, and reliable weather warnings and forecasts are essential to our collective well-being, but also to the nation's ability to recover and to prosper. Now, I've emphasized how unusual this year is, but as we all know, a single year can be an anomaly. Is that the case here? What are we documenting across years, and what might we expect in the future? Well, if we look at the reinsurance agency, Munich Re tells us the frequency of extreme events has risen steadily over the past 20 years. The number of meteorological and hydrological events each tripled during that 20-year period of time. The IPCC recently released its special report on the risks of extreme events and disasters. And in short, this report says that we can expect more of many of these types of extreme events. And here's what the report says about 5 types of extreme events, ordered by how certain we are of the prediction. Number 1, and I quote, "It is virtually certain that increases in the frequency of warm daily temperature extremes and decreases in cold extremes will occur throughout the 21st century on a global scale." Number 2, it is very likely that heat waves will increase in length, frequency, and/or intensity over most land areas. 3, it is very likely that average sea level rise will contribute to upward trends in extreme coastal high water levels. 4, it is likely that average maximum wind speed of tropical cyclones, typhoons and hurricanes, will increase throughout the coming century, although possibly not in every ocean basin. And finally, 5, it is likely that the frequency of heavy precipitation or the proportion of total rainfall from heavy falls will increase in the 21st century over many areas of the globe. In a separate study, a paper from the White House Office of Science and Technology Policy tells us that it's very likely that large-scale changes in climate have influenced and will continue to influence many different types of extreme events, such as heavy rainfall, heat waves, and flooding. Large-scale climate change is also likely to affect small-scale phenomena like severe thunderstorms and tornadoes, but the nature and the degree of that influence are very uncertain, especially for tornadoes. These patterns only underscore the importance of enhancing our ability to predict and manage these events. I show you again this slide of the disasters because I want you to pay close attention and examine the extreme events here. You'll see they run the gamut from highly localized and brief events like tornadoes to region-scale weather events like hurricanes, snow, flooding, where we can provide a longer lead time to prepare, to climate-scale events like the drought in the southern plains of Texas, Oklahoma, and Louisiana, where we can watch the conditions develop over multiple weeks. These events have different underlying physical drivers. Therefore, to observe, monitor, predict, and manage the impacts of these events requires understanding everything from the vertical wind profile at one individual location in order to predict favorable tornadic conditions, to large-scale weather patterns which stretch around the globe, for example, ones that might block or blocking patterns that might bring on heat or cold waves or drought. This means that we need diverse observations from a variety of platforms, from weather balloons, radar, satellites, networks of soil moisture sensors, ocean temperature sensors, and so on. Understanding and predicting and managing extreme events requires an extraordinary amount of information about the physical state of the Earth system and how it's changing from moment to moment as well as decade to decade. I believe that one essential key to meeting this challenge is what we are coming to call critical environmental intelligence. Just like intelligence in the security world combines data, information, analysis, modeling, and assessment, so too does intelligence in the environmental arena. NOAA is the nation's trusted broker for weather and climate data, information, and warnings. NOAA provides weather and climate products and services on every temporal scale from minutes to decades, and on every spatial scale from neighborhoods to global. Environmental intelligence is needed on each of these different spatial and temporal scales because decisions are made. Let me highlight 3 categories of services that NOAA provides. 1, we provide forecasts for short fuse events such as tornadoes, heavy rains, heat waves, like the extremes we experienced in every state this summer, or solar storms, which are becoming more frequent, with impacts on GPS, air travel, electric power distribution, and more. Tornado warnings, for example, are issued on a timescale of minutes and down to the neighborhood space scale. 2, we track the progress of extreme events, such as the maturation of a tropical depression into a full-blown hurricane. NOAA's Hurricane Prediction Center tracks these potentially devastating storms at the regional scale, but also on a very short time scale. Another example, development of cold fronts in Colorado into lines of severe tornadic thunderstorms along the Gulf Coast. We also issue volcanic ash advisories to ensure safe air travel. And 3, we generate climate forecasts weeks to months in advance, such as droughts in Texas, Oklahoma, New Mexico, Georgia, etc. NOAA's Drought Monitor issues weekly reports of the current state of the drought across all areas of the country. Winter flooding events in North Dakota or the Ohio Valley last spring. NOAA's scientists contribute heavily to the National Climate Assessment and other national and international assessments, and these assessments provide authoritative and comprehensive review of the state of the science with respect to extreme events. They consider scales up to global and provide projections out to the end of this century and beyond. So the question is, given this diversity of temporal and spatial scales, how do we continue to improve our environmental intelligence? We do so by improving environmental observations, research, and modeling. And when I say we, I mean all of us. This is a joint venture. Improving weather and climate forecasts will require enhancing Earth observations from satellites and other platforms, bolstering computing capacity, transforming our coupled ocean, atmosphere, land models, and strengthening research to detect patterns in changes and understand the underlying causes of these changes. And of course, intelligence is only as useful as the capacity to use it. And so we must also pay attention to improving effective response to forecasts or warnings. This brings me to our concept of a weather-ready nation, one whose citizens, emergency managers, and businesses understand the value of the services provided and use them to make informed decisions. Improving decisions will rely upon social science research to understand how best to deliver timely, usable, and credible information. We need to know if people hear and understand the information we think that we're providing. Do they always respond in ways that protect themselves and their property? And if not, why not? So with that framework, let me focus on what we are doing to enhance both critical environmental intelligence and its effective use, and where we are facing some challenges. Environmental intelligence starts with observation systems: satellites, ground-based monitors, planes, ships, buoys, moorings, weather stations, tall towers, weather balloons, underwater gliders, and so on. The Earth is a big place. Our ability to reduce vulnerability to extreme events is dependent upon many factors, but most certainly on our ability to observe and monitor changes in the frequency and intensity of these events. Some of the major overarching challenges are to improve our ability to detect extremes reliably, to maintain the continuity of the observations, and to improve the interdependence of observing systems. For example, many of our in situ observation networks were built to observe weather. They don't have the long-term stability or the accuracy required for climate. During extreme events, it's often difficult to get consistent and robust observations. This is especially true for smaller scale events, such as hurricane precipitation, tornado, or severe thunderstorm winds, or hail. I believe that we are in need of new, cost-effective technologies to monitor extreme events. Satellites must have a sufficiently long overlapping period of record, otherwise there is a discontinuity in the data. Achieving this goal is increasingly challenging in light of the expensive satellites coupled with tighter budgets. To inform our decisions on which observing networks to invest in, we need to understand the current predictive value of each system at different levels of investment. For example, how much better are the predictions with twice as many observing points? How much worse are they with half as many? To get this information, we need to link observing systems with modeling experiments. Observing Systems Simulation Experiments, OSSEs, do just that. They are a powerful tool at our disposal. They are typically aimed at assessing the impact of hypothetical simulated data on a model or a forecast system. To ensure that modelers get the data they need, modeling requirements must be better communicated to the folks who design observing systems. Comparing multiple independent observing systems allows the scientific community to increase their confidence in the longer-term trends. And above and beyond having good observations, their analysis is critical. So what are some of the challenges we face in the data analysis arena? One opportunity that looms large is to make better use of multiple independent data sets, akin to using model ensembles. This slide depicts the use of multiple data sets, in this case, indicators drawn from essential climate variables. Now that's interesting. That slide didn't do what it was supposed to do. Let's try this again. I'm trying to get them all up here for you at once, but it's not going to let me do that, so you'll just have to watch them come up. Okay, so this slide depicts the use of multiple data sets, in this case, indicators drawn from essential climate variables. This graphic is based on the Bulletin of the American Meteorological Society's State of the Climate Report from 2009, with some modifications by NOAA's National Climatic Data Center, NCDC. It shows 10 key physical indicators of the Earth system. 7 of the 10 are going up and 3 are trending down, all consistent with a warming climate. For example, the ocean heat content is trending up and sea ice is trending down. Each indicator looks at multiple independent data sets. And this technique helps to increase the confidence in the data and mitigate the effect of some kind of structural or statistical errors. And you can see in each of the panels the number of data sets. So for a specific community, it says 3 sets of data. Or for temperatures near the surface, there are 7 different sets of data. Looking at multiple indicators is also helpful. Since the physical properties that the indicators are measuring are connected, it's not surprising that the measurements themselves are consistent with one another. This suite of indicators approach lends additional confidence that the measurement, understanding, and ultimately prediction of a vast, complex system. These graphs depict trends in annual averages, but of course, means exclude the extremes. So I'd like to next show you a way we can look directly at the trends that we're seeing with the extremes themselves. The indicator approach produces a useful tool for both monitoring and communicating the diverse and highly variable nature of extremes. What you see here is a graph of NOAA's U.S. Climate Extremes Index. A brief explanation of this is in order. The vertical scale is the percentage of the country that is affected by the various extreme events in the index, averaged over the unit of time on the horizontal scale, in this case January through October of each year. The red bars are the annual values. The green is a 5-point binomial filter with overlapping endpoints, and the black line is the average from 1910 to 2011. So this index includes the variables shown in the bullets, and it broadly covers extreme heat, cold, rain, drought, and landfalling hurricanes. This kind of index can help us answer questions from industry, from emergency managers, from infrastructure planners, and from the public, all of whom have strong interest in the current state of extremes, as well as what we might expect in the future. For example, notice the upward trend in recent decades. While the index has been high in the past, the change from about 1970 to the present day is quite pronounced and qualitatively different from the previous years. So what's driving this index up? What observations are contributing to the trend? Decision makers use this kind of information to help plan and manage their response to extreme events. So let's take a little closer look. Deconstructing the index reveals what is driving the trend. In this case, it's extremes in maximum and minimum temperatures, too little and too much water, and one-day heavy precipitation. These graphs are individual elements of NOAA's U.S. Climate Extremes Index. The vertical axes remain the same, the percentage of the country affected by a given extreme. All graphs, again, are from January to October, each year from 1910 to 2011. So these are the primary components that are driving the changes in the Climate Extremes Index. Extremes in maximum and minimum temperature, too much and too little soil moisture, and one-day heavy precipitation events. Extremes in minimum temperature mean unusually warm or cold daily high temperatures, either in the top 10% or the bottom 10% of maximum temperatures. You can visually see that since 1970, more of the country is experiencing unusually warm highs, which are the red bars, and less of the country is experiencing unusually cool highs, the blue bars. But more striking is the change in the extremes in minimum temperature related to unusually warm or cold nighttime lows. More of the country is experiencing unusually warm nights, and less of the country is experiencing unusually cool nights. Warm overnight lows are related to heat stress in both people and plants and animals. They never get a chance to cool off. So this data set is of particular importance to those managing response to extremes. What does the index tell us about too much or too little soil water? The green bars show the percentage of the country in extremely wet conditions, and the brown bars show extremely dry conditions. While the country has had periods of more severe drought, for example, during the Dust Bowl years of the 30s, we've never seen the country get both drier and wetter at the same time, as the graph shows has happened in the last decade. And finally, the one-day heavy precipitation graph shows more single days with precipitation much above normal, the top 10%. This is important for hydrological engineers, water resource managers, and emergency managers, especially in flood-prone areas, among others. A variety of observations taken over time and used in well-crafted ensembles can improve understanding and management of extremes. These observational data, our historic record, are the vital input to models critical to predicting and projecting the future state of the Earth system. Extremes occur on multiple scales. Modeling needs to match the time and space scales. Here we're looking at the observed versus modeled results for the severity of summer heat waves. This model was run by NOAA's Geophysical Fluid Dynamics Laboratory, GFDL. And as you can see, the climate models are beginning to resolve the key features of regional scale events such as heat waves. The output of global climate models often needs to be downscaled to be of greater use at regional and smaller scales. When global climate models are run on grids with large spaces between the points, they sometimes can't resolve features of interest to decision makers. Downscaling historically involved either nesting a regional climate model into a global climate model, dynamical downscaling, or using various statistical techniques to project the state of the system between the grid points. However, newer high-resolution models running on supercomputers can resolve much finer detail. Combined with established downscaling techniques, these new models are allowing modelers to perform right scaling, generating results at the right scale for the phenomenon of interest or the application of the results. As we saw earlier with observations, analyzing the results of ensembles of several models together allows modelers to improve predictive skill and also to evaluate the different characteristics of different models. An overarching challenge is to focus modeling activities on topics of particular societal interest, like extreme events, and at timescales that are relevant, highly relevant to decision-making. The seasonal timescale is particularly important to agriculture, for example, and to water managers who need to plan their resources for the upcoming seasons. The decadal timescale is critical for the infrastructure planners and for the construction and some insurance sectors who need accurate pictures of the likely climate in 10 to 30 years. As I pointed out earlier, many sectors of society are vulnerable to changes in weather and climate, particularly the destructive effects of extremes. So in order to make sound decisions, people need to know what the trends are in these types of events and the extent to which human activity may be affecting the trends. So let's next take a look at what influences our ability to detect trends in extreme events and attribute any changes to various causes. The current state of science for detection and attribution of changes in extremes varies greatly by the type of event. This graph is the result of a series of workshops that NOAA convened to investigate the state of the science for detection and attribution of trends in extreme events. This graph is based on papers summarizing the findings of the workshops, some of which are in journal review, for example, in the Bulletin of the American Meteorological Society. The circles represent the various types of extremes considered at the workshops: extreme storms, heat, cold, drought, and floods. Each type of extreme event was evaluated for the adequacy of our current level of physical understanding of what might be driving the changes. And each event was also evaluated for the adequacy of the available data to detect changes, including trends. So, for example, we have a relatively good understanding of what can lead to changes in heat waves, and our data are fairly adequate to detect changes in heat waves over time. However, with ice storms, both our physical understanding of what factors would affect a trend and our data on their frequency of occurrence and intensity are much less adequate. Dr. Ken Kunkel of the Cooperative Institute for Climate and Satellites reported earlier this week on our present understanding and ability to detect trends in heat waves and extreme precipitation events. Climate or long-range forecasts look ahead weeks to months. These are the forecasts that people, communities, and businesses need to prepare for many extreme conditions. These are the tools that are critical for communicating both uncertainty and risk. We know how very useful some of these tools have been and can be because they've been used recently. For example, long-range flood forecasts helped us warn Minot, North Dakota, as early as November of last year, of intense winter and spring floods on the horizon. Long-range drought forecasts in Texas warned state fire managers as early as last December that helped pre-position firefighting assets and resources so that first responders could act quickly when the fire season arrived. And we know that more and more communities are looking for and using decision support tools to plan, for example, to adapt to a climate-influenced future. Again, 2 examples. NOAA data are being used by the New York City Panel on Climate Change to plan and prepare for sea level rise and flooding caused by coastal storms. The New York City Department of Environmental Protection is raising pumps at the Rockaway wastewater treatment plant from 25 feet below the existing sea level to 14 feet above the existing sea level as a result. A second example, Boulder, Colorado is using NOAA data and climate models to manage their water future. Businesses also use climate forecasts and data strategically. 3 examples here. The U.S. home building industry estimates savings of more than $300 million per year in construction costs from using just one of NOAA's climate tools related to freezing and frost depths. 2, the U.S. Department of Agriculture uses NOAA's climate information to develop regional, national, and global crop outlooks that provide the agricultural industry with information about conditions that may impact crop production. And finally, Pacific Northwest oyster hatcheries are using ocean acidification data in real time to protect oyster larvae from seasonal corrosive waters, which in turn protects seafood production and jobs. Another decision support tool to facilitate long-range planning and climate adaptation is NOAA's Digital Coast tool, shown here depicting sea level rise impacts viewer tool. Users can see the potential physical, ecological, and socioeconomic impacts of sea level rise in order to inform the planning efforts of community officials and coastal managers. This tool is the basis of a new partnership with the U.S. Department of Housing and Urban Development to better understand and prepare for the potential impacts of sea level rise on vulnerable populations, infrastructure, and ecosystems in places such as seen here with Galveston, Texas. So what's likely down the road on the weather-climate front? Increased overall warming, an amplified water cycle, more extreme events and more variability, more wild weather and wild swings in weather. As the nation's requirements for environmental intelligence continue to grow, 2 things happen. First, the number of users of this information grows. This creates new markets that can be exploited by commercial companies that add value to the otherwise free data that agencies like NOAA provide. And second, as the amount of data increased dramatically, our ability to assimilate the data into decision-making is tested and reminds us of the need to innovate to meet this rising demand. Our experiences with federal budgets last year and this year are likely a harbinger of the challenging times ahead for sustaining and improving our abilities to predict and therefore to manage extreme events. I can tell you that I think the road ahead is fraught with great uncertainty. Observing systems, research, high-performance computing are all absolute prerequisites to producing weather and climate forecasts, and all of these are at great risk. We need to make sure that the current economic and political landscapes don't erode our ability to provide accurate, reliable forecasts. The nation's need to understand, predict, and manage our responses to weather and climate extremes exceeds the scope of any individual organization or government agency, and so collaboration is vital. Our partnerships with academia, industry, other federal agencies, and the international community and the cornerstones for successfully securing environmental intelligence that we need in the future. I believe that we have some major challenges ahead. We will be doing our utmost to make the best case we can for the importance of these and other programs, and we need your help in continuing to articulate why this is so important and vital for our nation's future. There is a strong role for AGU in promoting and supporting partnerships, in supporting scientific integrity, and in together defining what our future will look like. Thank you for this opportunity to share a few thoughts on extreme events with you, and I'm happy to take any questions. Thanks.
Thank you, Jane, for that very informative and inspiring presentation. We do have time for some questions. There are microphones in the aisles, and so please step up to one of those, and we'll start the Q&A. Can we dim up the, turn up the house lights, please, so we can see people? See people? Yes. Can we turn up the lights, please? Look.
Eventually.
Eventually, yes. It looks good. Well, okay. Is there a question over here? No? Okay.
Dr. Lubchenco, thank you for your talk. You mentioned having a weather-ready society, and I think one of our biggest challenges is the communication of risk. And I'd like to use an example of the tornado super outbreak this spring in Arkansas, Alabama, and Tennessee. And that was an event that was very well forecast and very well warned, both many days in advance and on the day of the event. But we still had a large loss of life. And so I'm wondering what your thoughts are on how we can improve our communication of risk and also improve our citizens' action related to that risk.
That's a great question. Can you tell me who you are? And everybody, will you introduce yourselves, please?
Oh, yes. My name's Maura Honenberger, and I'm an atmospheric scientist at the University of Utah.
Great. So great question. Thank you very much for that. And I think tornadoes are a super example of exactly this. We did unfortunately see a very large number of deaths from that amazing number of tornadoes that we had. I think in April alone there were something like 814 tornadoes, all-time record for any single month. And we were, in fact, able to issue warnings quite many days in advance, especially because of the information from our polar orbiting satellite that's up there now, POSE, that helped give us alerts that conditions were developing that would be conducive to tornadoes. We did get the word out, and as you noted, despite that, there was significant loss of life. I think that there are many contributors to that, and in fact we are in the middle of doing some intensive investigations to really understand, get some data and really understand what those causes are. I think they will turn out to be multiple different causes. Some of the communities that I visited right after the tornado hit Tuscaloosa, Alabama, the people in those communities told us that they were well aware that tornadoes were on the way, but they did not have any place to go. They didn't have shelters. This is particularly true in some communities, especially with trailer parks, for example. And I think it highlights the need to not just have warnings, but for communities and emergency managers to have options for people to have some sort of safe haven. If you are in a house and have a basement, that's certainly one option. If you are in a trailer, that's a completely different situation. So that's certainly one thing. Other people told us that they had heard so many warnings that they just kind of tuned out and didn't pay attention. And I think that is will be a continuing challenge for many. And it underscores the need for, I think, more social science research to understand what people are hearing when warnings are issued and how not to have either tornado fatigue or hurricane fatigue where people just start tuning out because it just, in a past experience it didn't result in a disaster and so they think maybe it's not going to be that bad. So I think there are a number of causative agents. We need to understand what those are before designing the remedies. I've highlighted a couple of them that I've heard personally from visiting some of those communities. And one of the purposes of this new effort that we are launching, Weather Ready Nation, is to do pilot projects in a number of places around the country to really have the dialogue with the community leaders, with the emergency managers, with those who are responsible for getting people out of harm's way, to understand better how we can deliver information that will be understood and used and keep people out of harm's way as much as possible. Question here?
Ma'am, thank you for a great discussion. I'm Bob Morris with AER. Could you comment on NOAA's interests and efforts in extreme space weather? Space
weather is a very interesting phenomenon. As I think everyone is well aware, there are, the sun goes through different cycles where there are periods of enhanced activity called solar maxima. We are entering a period of enhanced activity, which simply means that the likelihood of energy coming from the sun increases. The thing, even though solar cycles are cycles from what we know, something that is distinctly different about the solar maximum that we are entering now from earlier solar maxima is the increased vulnerability of our society to electromagnetic radiation coming from the sun. Our technologies are so much more vulnerable, from the electrical grid to our GPS systems to polar flights and communications at the poles, that there is increased concern that extreme solar events might in fact have significant devastating impacts on the U.S. This underscores the importance of having early warning systems. Currently, we rely on a single satellite, a NASA satellite called ACE that's at the L1 position to give us warning about incoming solar radiation. ACE is well past its expiration date. Everyone has fingers crossed hard that ACE will continue to perform, but that's not really a smart thing for the country or the world to rely on, which is why in our budget requests for last year and this year, we included requests to refurbish and launch ACE's replacement, Discover. We did not get in our FY12 budget the full amount that we requested, which was $47 million, but we did get $30 million, and I think Congress is appreciating how important solar weather might be. So we will begin to move ahead with that project. But I think this is an area where there is insufficient general public attention and a lot of very interesting science, as well as plans that need to be in place for dealing with severe solar storms should in fact they happen. Next question.
Thank you so much for your comments today. My name is James Arnott at the Aspen Global Change Institute. I'm wondering, you described very eloquently how science is becoming more serviceable and relevant to policy and decision making. I'm wondering if you could comment on how we protect the scientific community. I'm thinking about the incident that's unfolding in Italy with respect to the seismologists in the town L'Aquila, and using that as maybe a cautionary tale for the rest of the world. How do we protect the scientific community?
Obviously, I believe it's important that scientists share the information they have and that we do the best possible job of communicating not only what's known but what's not known and how certain we are of information. Communicating risk and uncertainty are something that continue to be challenging, and I think we will continue to work toward ways of better doing that communication. But I can tell you that not only in Italy, but a lot of other places around the world, there is increased discussion, at least, underway about scientific information. I was in Japan about a month ago, and there is intense discussion by the Japanese people about what they are calling the 3/11 event. Specifically, how can we trust scientists, a number of reporters asked me, when scientists told us that nuclear energy was safe. And so I think there's a lot that gets lost in the translation, and we need to pay attention to doing a better job of communicating risk and uncertainty while not burying warnings about important phenomena with so many caveats that people don't understand what we're saying. So this whole area of communicating risk and uncertainty is I think, front and center and is important for all of us to be paying attention to. Far left over here, yes.
Yeah. My name is Alexander Uzmaikin from Jet Propulsion Lab. Your presentation is focused on societal definition of extremes.
Yes.
Damage, dollars, and stuff. But extremes can happen nowhere with no damage. So there is scientific approach and definition of extremes. In that sense, my question is close to the previous one. So are we neglected those scientists who study fundamental approach to extremes and would be allocated more resources for that, not only protection in a physical sense, but also protection in support of this science, which might be societal later, but not today?
I believe that, what I was focusing on in my remarks is what is part of NOAA's mission, which is to advance scientific knowledge and then use that to provide services like warnings about extreme events to the American public. I completely agree that there are other types of important extreme events and that those are important for us to understand and to study, but that's not part of what we do at NOAA, which is what I was focusing on. Okay?
My
Yes.
name is Witold Krajewski. I'm a professor of engineering at the University of Iowa. I'm a hydrologist, and also I'm the chair-elect of QUASI. QUASI is the consortium of universities for the advancement of hydrologic science, a group of over 100 US universities. In your talk, you mentioned floods. In your talk, you mentioned the need for partnership between NOAA and academia. And as far as I know, there are several cooperative institutes in the areas of atmospheric and oceanic sciences. I do not know of any between NOAA and hydrologic sciences. Do you have any specific plans to address this?
NOAA has some of the responsibilities for hydrological information. So too do USGS, Geological Service, and the U.S. Corps of Engineers. And the three agencies have recently signed a memorandum of understanding to work cooperatively together on a program that is called IRIS, the Integrated Water Information Sciences and Services, or some combination of words like that. You learn the acronyms and you forget what they mean. And that is intended to be a partnership with the academic community as well. It's still unclear how that is going to evolve, what the opportunities are. I would encourage you to communicate with some of the NOAA hydrologists whom I'm sure you know in some of our hydrological centers. I would love to have lots more cooperative institutes, but I can tell you that with the pressure on our budgets, that's probably not going to be the direction we're headed. And I think that just a word to everyone, we are really facing some very, very tough times, and there are lots of things that we would like to be doing that we won't be able to. And we have some very tough decisions ahead. But to the extent that you all can help us understand what the opportunities are and what's important and help us articulate that case, I think that will benefit everyone. So you've been very patient. I'm sorry we don't have time for all of the questions. Is that? So thank you all for attendance at the meetings and for your great questions. Thanks.